Good day everyone. This project focuses on the application of forensic chemistry in fire and arson investigations. Forensic chemistry uses chemical principles and analytical techniques to analyze evidence related to criminal cases. Common evidence includes fire debris, fibers, explosives, drugs, and toxic substances. In arson investigations, evidence is often damaged by heat and combustion, making analysis more challenging. Therefore, advanced analytical techniques are needed to identify physical and chemical changes in the evidence. In this study, two analytical techniques were used, which are SEM-EDX and UV visible spectroscopy. SEM-EDX help observe microscopic surface damage, fiber degradation, and charring effects on burnt materials. Meanwhile, UV-based spectroscopy measures light absorption to determine the concentration of chemical substances based on the Beer-Lambert law. In this experiment, burnt cloth was analyzed using SEM-EDX, while methylene blue solutions were analyzed using UV-based spectroscopy. For sample preparation, two types of forensic evidence were prepared, which are burnt cloth as solid evidence and methylene blue solution as liquid evidence. Burnt cloth was selected because textile materials are commonly found in fire scenes and can provide information about thermal damage and residue formation. Methylene blue was selected because it is a colored compound that is suitable for UV-based spectrophotometric analysis. For UV-based analysis, standard methylene blue solutions with concentration of 0.01, 0.03, 0.05, 0.07, and 0.1 were prepared using distilled water together with a sample with unknown concentration. Distilled water was also used as the blank solution. For the SEM analysis, two cloth samples were prepared, which were unburnt cloth and burnt cloth. The clean cloth was cut into equal pieces and one piece was partially burnt to simulate fire evidence. The sample was then cooled, cleaned gently to remove loose ash, and cut into smaller pieces before SEM analysis.
I will explain the methodology used in this analysis. For UV spectrometer, the analysis was carried out to determine the absorbance of methylene blue solution and its unknown. Before the analysis, the spectrometer was calibrated using distilled water as the blank solution. Firstly, each standard methylene blue solution was transferred into the cuvette for measurements. Next, the absorbance was measured at 664 nanometer because methylene blue show maximum absorbance at this wavelength. And then a calibration curve was plotted using the concentration against absorbance based on the Beer-Lambert law. Then, the equation obtained from the calibration curve was used to determine the concentration of the unknown methylene blue sample by substituting its absorbance value into the equations. For SEM methodology, the prepared unburned and burnt clothes sample were carefully placed into the SEM chamber for analysis. During the process, the electron beam scanned the sample surface to produce clear image for burnt fiber and residue. The morphology of the burnt clothes was then observed at different magnification to study the physical and structural changes caused by the combustions. Several characteristics were observed, carefully including the crack, broken fiber, melted area, and also char formations. This observation helped to identify the effect of burning on the cloth structure. After the analysis was completed, the SEM's instrument was then switched off properly and then the sample were removed from the chamber. Next, this is the result of both analyses. First, UV-based analysis. The table shows the absorbance obtained in the analysis on the standard and also the unknown concentration of the methylene blue, and a standard curve was then plotted to get equation to determine the unknown concentration of methylene blue. This slide also shows the calculation to get unknown concentration, which is 0.08 mm. This is the result that have been observed on the burnt clothes and also unburnt clothes using SEM at 30, 100 and also 500 magnification.
Next is discussion for UVVs. First, the adsorbent concentration relationship show that the adsorbent increased from 0.26628 for the 0.1 nm standard solution to 3.08484 for the 0.10 mm standard solution. This trend follows the Beer-Lambert law, which states that the adsorbent is directly proportional to concentration. As the concentration of methylene blue increased, more light at 664 nm was absorbed by the solution. Using the calibration curve, the concentration of the unknown sample was determined. The unknown sample recorded an absorbance of 2.84804, which corresponds to a concentration of 0.0804 nm. since the value falls within the calibration range and lies between the 0.07 and 0.10 mm standard. It confirmed that the calibration curve method was accurate and reliable for quantifying the unknown sample. From a forensic perspective, UV spectroscopy is a rapid, non-destructive and reliable analytical technique. It is particularly useful for analyzing colored liquid sample and allowed forensic chemists to identify, compare and estimate the concentration of unknown substance encountered during investigation.
For the discussion part, looking at the SEM result of sample B, the unburned fabric shows a highly systematic, tightly woven yarn matrix at the lower magnifications. Zooming in to 500 times magnifications, the individual fibers appear remarkably smooth, continuous and non-porous with a uniform cylindrical profile. The complete absence of natural surface irregularities confirm that this is a synthetic polymer, specifically polyester. When exposed to the flame, the burnt samples completely shows different results. At the lower magnifications, the orderly woven grid is entirely disrupted, showing extensive melting, fiber fusion and hardened shell blocks. At 500 times magnifications, we can see that a total mid-structural collapse. The fiber have congealed into irregular globs with subatomic cracking and microvoids. In forensic, these predictable thermospastic changes are vital because they allow us to map the heat intensity, locate the fire point of origin, and clearly differentiate accidental thermal changes from intentional or high-intensity arson.
Conclusions: UVV's analysis successfully determined the concentration of the unknown methylene blue sample, which was 0.0804 millimolar. This demonstrates the effectiveness of UVV spectroscopy for quantitative analysis of liquid evidence. Next, SEM imaging identifies significant thermal degradation in burnt polyester fibers, including morphological change, provide valuable information regarding the effect of fire damage on the material. Both techniques provide reliable forensic evidence through quantitative and morphological characterizations. Therefore, UVVs and SEM are valuable complementary tools for forensic investigations and fire damage analysis.